Welcome to the technical module for using the AMD Vitis Model Composer Hub Block. Here is the agenda for this technical module. We'll first introduce the AMD Vitis Model Composer Hub Block. We'll then go over how to use the block to select hardware, generate code, analyze and verify a design, and finally validate on hardware. The Vitis Model Composer Hub Block plays an important role in the Vitis Model Composer design flow. Once you create a design and simulate for functional verification in the Simulink environment, you need a Vitis Model Composer hub block to analyze the design, run hardware validation for the design, and export various outputs from the design. Vitis Model Composer automatically compiles designs into low-level representations. However, a Vitis Model Composer model requires the addition of the Vitis Model Composer hub block to configure compilation and generate outputs. The block allows you to have many design-level controls, such as selecting output directories, the compilation types, and the types of analysis. It is also used to select the target hardware or the platform for the design. Let's briefly look at the Vitis Model Composer hub block. The Vitis Model Composer hub block controls the behavior of the Vitis Model Composer tool. You can specify a targeted design flow for the generated output, the directory path for the output, and the desired device and design clock frequency. The hardware selection pane helps with the device, board, or platform selection. The code generation pane provides options to select the output flow by selecting subsystems and specifying the code directory. Different options will be displayed depending on whether the subsystem is targeting HDL, HLS, or AI engines. The setting pane lets you specify whether the Vitis Model Composer hub block should treat your model as a legacy system generator design. Now let's look at the hardware selection flow. Vitis Model Composer hub block provides a convenient way to select the hardware for your design via the hardware selection pane. The Select Hardware option leads to the Device Chooser dialog box, which displays a list of available parts, boards, and platforms that are supported by the Vivado IDE database. Once you have selected a target device, Vitis Model Composer can use the device data from the Vivado IDE database to optimize your design for the specific hardware platform. Now let's look at code generation. In the Vitis Model Composer hub block, the code generation pane provides options to select the output flow by selecting export type for a selected subsystem and specifying the export directory. Generating the code for the HDL includes tabs for the settings, analyze, validate on hardware, and export. The settings tab includes the following options: target language. This specifies the HDL language to be used for compilation of the design. Synthesis strategy. This allows you to choose one of the predefined synthesis strategies. Implementation strategy. This allows you to choose one of the predefined implementation strategies. Enable multiple clocks. This setting must be enabled when the design has multiple clocks. This indicates to the code generation engine that the clock information for the various subsystems must be obtained from the respective clock tabs. FPGA clock period in nanoseconds defines the period of the system clock. The period is passed to the implementation tools through a constraints file where it is used as the global clock constraint. Simulink system period in seconds defines the Simulink system period. The Simulink system period is the greatest common divisor of the sample periods that appear in the model. Clock pin location defines the pin location for the hardware clock. This information is passed to the implementation tools through a constraints file. The clock enable clear pin option instructs the tool to provide a CE_CLR port on the top level clock wrapper. The Analyze tab includes the following options: target directory. This specifies the work directory for performing the actions on this tab. Perform analysis option. This specifies whether analysis, timing, or resource will or will not be performed on Vitis Model Composer design when it is compiled. Analysis type. This offers timing or resource type analysis. Block icon display. This allows you to specify the type of information to be displayed on each block icon in the model after compilation is complete. And create interface document. When this checkbox is selected, the tool creates an HTML document that describes the design being netlisted. The Validation on Hardware tab includes the following options. Target directory. This specifies the work directory for performing the actions on this tab. Hardware system type. This allows you to choose between a bare metal or Linux hardware validation flow. The target option specifies the target for the hardware validation flow. It can be hardware or hardware emulation. You can also choose to generate a boot.bin file for a bare metal hardware system or an SD card image for a Linux hardware system after code generation. The Export tab includes the following options. Export directory. This specifies the directory where the export products will be created. Export type specifies the types of export products. Generate test bench. This instructs the Vitis Model Composer to generate an HDL test bench. Here's the list of supported compilation export types for HDL designs in Vitis Model Composer. The IP catalog export type allows you to package a Vitis Model Composer design into an IP core that can be added to the AMD Vivado IP catalog. The hardware co-simulation export type produces a design for device hardware that can be used in the loop with Simulink simulations. Note that if the target board is supported for hardware co-simulation, then the option is enabled in the Vitis Model Composer HubBlock dialog box. Otherwise, it will be disabled. The synthesized checkpoint export type generates a synthesized checkpoint file that can be used in a Vivado IDE project. The HDL netlist export type produces HDL files that implement the design. The Vitis hardware kernel export type generates code for the HDL subsystem and compiles it into an XO file using Vitis HLS. Generating the code for HLS subsystem includes tabs for the Settings, Analyze, and Export. The Settings tab includes the following options. FPGA clock frequency. This specifies the speed at which the device operates. It is specified in megahertz and passed on the downstream tools for implementation. Throughput factor. This determines the number of samples processed per clock cycle. A higher factor increases hardware resource usage, but also increases the overall processing speed. Test bench stack size. This determines the amount of memory allocated for test bench execution. If the default stack size is insufficient, you can increase it to prevent a segmentation fault error during execution. The Analyze tab includes the following option. Target directory. This specifies the work directory for performing the actions on this tab. The Export tab includes the following options. Export directory. This specifies the directory where the export products will be created. Export type specifies the types of export products. Generate test bench. When enabled, Vitis Model Composer generates the test vectors while generating the code. Here's the list of the supported compilation export types for HLS designs in Vitis Model Composer. HLS C++ code, when selected, the tool first simulates the model, then generates the code, and places the generated code file in the folder that was specified in the code export directory setting. IP catalog. When selected, the tool first writes the C++ code as described previously. It then synthesizes RTL code from the C++ code. Finally, it generates the packaged IP for use in the Vivado IP catalog. When generating the code for an AI engine subsystem, there are various tabs from which you can configure different parameters. From the Settings tab, you can specify a cell array of AI engine compiler options using the AI Compiler Options Edit button. This provides a method to control the compiler debug options, execution target options, file options, and so on. The Analyze tab includes the following options. Target directory specifies the work directory for performing the actions in the tab. AIE Simulator Options provides the ability to pass additional command line options to the AI Engine simulator. The Simulation Timeout option, when enabled, specifies the number of cycles for which AIE simulation is run. The Collect Trace Data for Vitis Analyzer, viewing internal signals and latency option, when enabled, collects trace data for signals within the AI Engine design to be viewed in the Vitis Analyzer or the Simulation Data Inspector. The View AI Engine Simulation Output and Throughput option opens the Simulation Data Inspector for plotting the outputs of the AI Engine subsystem as simulated by the AI Engine simulator. The Open Vitis Analyzer option invokes the Vitis Analyzer tool. This option is only enabled after AI engine simulation has been ran at least once after enabling. The Validation on Hardware tab includes the following options. Target directory specifies the work directory for performing the actions in the tab. Hardware system type allows you to choose between a bare metal or Linux hardware validation flow. The target option specifies the target for the hardware validation flow. It can be hardware or hardware emulation. You can also choose to generate a boot.bin file for a bare metal hardware system or an SD card image for a Linux hardware system after code generation. The Export tab includes the following options. Export directory specifies the directory where the export products will be created. The export type specifies the types of export products. And when the Generate Testbed option is enabled, Vitis Model Composer generates test vectors while generating the code. Here is the list of the supported compilation export types for AI engine designs in Vitis Model Composer. Graph code, when selected, the tool exports the AI engine subsystem as AI engine graph code. Vitis subsystem, when selected, the tool exports the AI engine subsystem as a compiled Vitis subsystem. Now let's look at analyzing and verifying designs. To help verify that your Vitis Model Composer HDL design will work correctly when it is implemented in your target device, the following analysis tools have been integrated into Vitis Model Composer. Timing analysis to ensure that HDL files generated by Vitis Model Composer operate correctly in hardware, you must close timing. Resource analysis to ensure that the HDL files generated by Vitis Model Composer will fit into your target device, you may need to analyze the resources being used. When the target in the block parameters dialog box of the Vitis Model Composer hub block is HLS C++ code and the verification flow is enabled, Vitis Model Composer uses C simulation to verify the generated C++ code. The model is simulated in the Simulink environment, and the inputs and outputs are logged into the signals.stim binary file. Vitis Model Composer generates the C++ code and a test bench, tb.cpp, which contains a main function. The objective is to verify the results of the C++ simulation match the results of the Simulink simulation. In the case of a mismatch, the mismatched output signal name is reported as well as the actual and expected values. The result is a pass-fail returned by Vitis Model Composer. When the target specified in the block parameters dialog box of Vitis Model Composer Hub is IP catalog and the verification flow is enabled, Vitis Model Composer uses C or RTL co-simulation to verify the RTL output. Again, the objective is to verify that the results of the RTL simulation match the results of the Simulink simulation. In this case, the verification flow is as shown here. The result is a pass-fail returned by Vitis Model Composer. If the C simulation fails, the process stops before the C RTL simulation is run. The Verso Adaptive SoC AI Engine Simulator models the timing and resources of the AI engine array accurately when using transaction-level approximately timed System C models for the NOC, DDR, PL, and PS. This allows accurate performance analysis of the AI engine. Vitis Model Composer supports verification of the data flow graph using the AI engine simulator. To verify and analyze the AI engine design, use the Analyze tab of the Model Composer hub block. The Analyze button will generate and compile AI engine code from the design and run the cycle approximate AI engine simulation in System C. The simulation timeout value limits the execution to the specified number of cycles. The default timeout value is set to 50,000 cycles. On performing the Analyze option, you can monitor the compilation, simulation, and verification progress of the AI engine graph code from the progress window. After successful compilation and simulation, Vitis Model Composer automatically compares the target output with the golden output. When the AI engine code cannot be verified with a test pass message, you will need to debug it to arrive at the reference output. You can obtain profiling data when you run your AI engine simulation. Analyzing this data helps you gauge the efficiency of the kernels, the stall and active times associated with each AI engine, and pinpoint AI engine kernels whose performance may not be optimal. This allows you to collect data on design latency, throughput, and bandwidth. You can perform an event trace by using a formatted printf statement in the code for printing debug messages. To achieve this, enable the Collect Profiling Statistics and enable printf for debugging option in the Analyze tab of the Vitis Model Composer hub block. The Vitis Software Platform Analyzer is a utility that allows you to view and analyze the reports generated when building and running the application. It is intended to let you review reports generated by both the Vitis compiler when the application is built and the Xilinx runtime XRT library when the application is run. During the simulation of the AI Engine graph, the AI Engine simulator writes a summary of the simulation results called default.aierun_summary. This can be viewed in the Vitis Analyzer. The summary contains a collection of reports and diagrams reflecting the state of the AI Engine application. Vitis Model Composer integrates the Vitis Analyzer utility. The analyzer can be invoked by enabling the Collect Data for Vitis Analyzer option from the hub block, along with the AI Engine simulation. When the simulation completes, Vitis Model Composer automatically reads the system.wdb file, which is generated during the AI Engine simulator run, and invokes the timeline flow. From the Report Navigator, you can view other available reports, such as Summary, Profile, Graph, Array, and Log. You can also use the MATLAB command shown here to launch the Vitis Analyzer. Vitis Model Composer provides the capability to log the simulation data and visualize the output of an AI Engine subsystem by integrating the Simulink tool Simulation Data Inspector feature. It also calculates the throughput of each output port of the AI Engine subsystem. To achieve this, click the View AI Engine Simulation Output and Throughput option from the Vitis Model Composer hub block. When the AI Engine simulation completes, the tool automatically brings up the Simulation Data Inspector window, which reflects the output of the AI Engine subsystem as shown in the figure here. The Simulation Data Inspector displays available data in the Inspect pane. To plot a signal, select the checkbox next to the signal. You can modify the layout and add different visualizations to analyze the simulation data. You can also obtain the throughput information for each port from the Inspect pane. If required, you can reopen the Simulation Data Inspector by clicking the Simulation Data Inspector icon from the Simulink Editor toolbar. The AIE simulation is a cycle approximate simulation, which means it can be used to estimate the latency between input and output ports of the AI Engine subsystem. This latency calculation can be displayed in Vitis Model Composer. To achieve this, run AIE simulation from the Analyze tab of the Model Composer hub block with the Collect Trace Data for Vitis Analyzer option enabled. On the Simulink canvas, one input to the AI Engine subsystem and one output from the AI Engine subsystem must be selected. You can also select multiple signals on the canvas. By selecting the AI Engine compute latency options, you can visualize the latency table. If AI Engine simulation has previously been run on this design, Vitis Model Composer will display the first sample latency, last sample latency, and average latency between the two selected ports. Latency can fluctuate over the course of a simulation, but it generally converges to a stable value over time. The Simulation Data Inspector can also be used to plot and calculate throughput for signals within an AI Engine subsystem. To achieve this, first run AIE simulation with Collect Trace Data for Vitis Analyzer and viewing internal signals selected. Then, the signals must be selected by right-clicking and selecting AMD AI View in Data Inspector. You have the option to plot the signals at its source port, destination port, or both. These signals might differ in hardware due to latency, for example, buffers introduced in the signal. After making a selection, the selected signals then appear in the Simulation Data Inspector. As shown in the figure here, View Source and Destination is selected. Note the latency between the signals at the source port and destination port. Now let's look at hardware validation. The hardware validation flow for AI engines in Vitis Model Composer provides a methodology to verify AI engine-based applications on hardware. Vitis Model Composer provides the option to validate the generated hardware image targeting a specific platform for the Simulink model. This hardware image can then be run on a board to verify whether the results from hardware match with the simulation output. This image can be either bare metal or Linux based. This figure shows the topologies that are supported for the hardware validation flow. You can generate a hardware image for designs with only AI engine subsystems, designs with both PL and AI engine subsystems, or designs with only PL subsystems. To generate the hardware image from a Simulink tool design, you should have an expandable platform that is a file with the .xpfm extension. You can also create an expandable custom platform for a custom board and use it in Vitis Model Composer. Using the Vitis Model Composer hub block, you have a choice between creating a bare metal application or a Linux-based application for either a hardware target or a hardware emulation target. In hardware emulation, the Vivado simulator is used to simulate the PL portions of the design, and QEMU is used to emulate the host code for the ARM processor. As part of the creation of the hardware image, the input data samples that are fed into the design during simulation in the Simulink tool are collected. Likewise, the output data samples from the design are also collected. The input and output design data is packaged as part of the hardware image and downloaded to the hardware. The input data is fed into the design in hardware, and the output data is collected and compared with the output data from the simulation. This comparison is done by the processor and the device. Unless something is wrong, the result should match bit by bit with the results of the simulation because the simulation in Vitis Model Composer is bit accurate. The hardware runs independently, and during the hardware run, no information is communicated between Vitis Model Composer and the hardware. Review the following design considerations for the hardware validation flow for AI engines and PL designs. In summary, AMD Vitis Model Composer automatically compiles designs into low-level representations using the Vitis Model Composer hub block. The Vitis Model Composer hub block controls the behavior of the Vitis Model Composer tool. Support for exporting different compilation types provides the freedom to choose a suitable representation for a design's environment. Enable the verification flow for HLS design by selecting the Create Test Bench and Run C Simulation or C RTL Co-Simulation options from the Vitis Model Composer hub block. Verification of AI engine code can be done via the Vitis Model Composer hub block, profiling, and event tracing, as well as using the Vitis Analyzer tool to calculate throughput. And finally, hardware validation flow can be performed by generating a hardware image targeting a specific platform for the Simulink environment. And this concludes our technical module on the Vitis Model Composer hub block. Thank you for watching.